So till now, we have looked at the extensions in the form of how players can randomize. So in the case of pure strategies, they don't randomize at all. Or we can say that the randomization is degenerated, it's only deterministic. Then in the case of mixed strategies, they arbitrarily mix by, but you may only mix your strategies and that may not depend on what others do. Now, in the case of correlated strategies, there is some dependent signals that the players get, and then a player randomizes given that signal. So basically the signal, formally the signal that there is a random, there is a probability space. Now the player, based on the drawn sample, the player gets a signal based on her information set. So the signals are correlated because they're based on the same probability space, but they're not the same, they're not necessarily the same. So the players get correlated signals, and the cross-correlated randomization requires any kind of randomization with any kind of interdependence, and we don't do it here, besides a little bit on the tutorial. Now, these are all about how you randomize, but all those, despite that they allow for some dependency when randomizing, the deviator was always a single person, which considered only interest. So there is a certain profile which can be somehow dependent on what others do, but the question is, should I deviate to improve my own utility? Now, another direction of extension is not looking necessarily at on randomization, but looking at group deviations. So you look at how can we protect which profile is stable against groups that deviate that want to improve, or at least not to harm anyone in the group. Formally, a profile is K-strong if for any, it's a K-strong Nash equilibrium, if for any set, or for informally that means that it's no set of size up to K can profitably deviate. Formally, it means that for any set which size up to K, if there is a profile such that the elements of that set can deviate, and nobody in that set suffers, then nobody in that set can strictly gain. Again, so if there is a profile such that, so profile is this K-strong in Nash equilibrium, if for any K, if for any subset of size at most K, therefore the subset cannot profitably deviate, which means that formally, if you have a deviation such that no player strictly suffers, then it means that also nobody can strictly gain. In other words, a deviation is profitable when nobody strictly suffers and at least one person strictly gains. And here we say that there is no profitable deviation. So if nobody strictly suffers, then there has to be no one who can strictly gain. That's what it says. So that's the definition. And when there is, that's a generalization. So when there is a one strong Nash equilibrium, it means that no set of at most one player can deviate, such that if nobody suffers, then there is nobody who can gain. In other words, nobody can gain from unilateral deviation. So one strong Nash equilibrium is just a Nash equilibrium, and an strong Nash equilibrium, so when no coalition at all can profitably deviate, such a strong Nash equilibrium is called just strong. And let us look at a simple example. So let us look at the coordination game, which is non-homogeneous. So we have two different Nash equilibria. I'm talking about pure now, only pure. Top left, excuse me, when everyone gets 1, and bottom right when both get 2. And there is only one strong Nash equilibrium bottom right, because top left is not strong, because they both can deviate, one to bottom and another to right, and they both will even strictly profit. It's enough that nobody suffers and one at least strictly profit. So there is only one strong Nash equilibrium. The price of anarchy, what is that? It's the best possible profile, 2 plus 2. The best possible profile divided by the worst possible Nash equilibrium, 1 plus 1, and that's 2. So the best possible profile is most twice better than the worst possible Nash equilibrium, but the best possible profile is itself a Nash equilibrium, so the price of stability is actually 1. So there is an optimum Nash equilibrium, but there is also a twice smaller than, twice less good than optimum. Now, the strong price of anarchy, however, and of course the strong price of stability, is only 2 plus 2 divided by 2 plus 2, because only the bottom right profile is left. So only the socially optimum profile is left as a strong Nash equilibrium, and it's only 1. So the price of anarchy has improved in the sense that it has become smaller. In general, the price of anarchy can become only smaller when we go to strong. It can only improve because we have now less options to look at the worst from, and the price of stability can only get worse in the sense that the price can only rise because we have now less options to get the best from. So that's the general observation. And having equated ourselves a bit with K-strong Nash equilibria, we are going to the last topic of today's lecture, and that's evolutionary equilibrium. Now that's only just a small glimpse on the evolutionary game theory, which is a very important part of game theory. And famous people like Maynard Smith work with that area. That's a very important part, and I definitely encourage you to learn more. Now we're going to look at only one of the very simplest part of that, and that's, excuse me, let me fix a typo. So we adapt Nash equilibria one second please. So we start with Nash equilibria and adapt it to what happens if we have population which is meshed randomly uniformly in pairs. So you play against other players, depends what strategies they have, and you want to see which strategy is stable, in the sense that if everyone plays a strategy, then no mutant, no small subset which change the strategy can outplay the others. Formally, look at action set B, and the fitness is described by at the following symmetric game. So I have two players, because we're going to look only at those couples which are randomly matched. So they play against the other, one against the other. They both have the option B, so they're both symmetric, so the same population. The utilities are symmetric, so what player 1 gets is just what player 2 gets, simply from the opposite point. So player 1, when player 1 plays X and player 2 plays Y, gets the XY value of some function, and player 2, when player 1 plays X, player 2 plays 1, gets the YX value of the function. So there is one function which actually describes what's going on, and the evolutionary equilibrium. Now we're going, the important part here is how we model. I want to show you the logic of why this definition is what we use. So the evolutionary equilibrium, and as I already mentioned, we also follow here the Osborn and Rubinstein book. So the evolutionary equilibrium models the state where everyone X according to some action X, and any mutant, so any population of mutants, not only one, any population, a small population of mutants which have another action would die out. So formally, if there is a fraction epsilon, some positive but small, arbitrarily small function, or let's say small enough, in the sense which we are going to define soon, if that function mutates to action Y, when the rest keep action X, well, this probability 1 minus epsilon, the mutant is faced with a player, is paired with a player who plays X. So the mutant obtains Y of YX. This probability 1 minus epsilon. And this probability epsilon, the mutant is faced with another mutant. So it's epsilon times Y1. U of Y1. While a non-mutant receives this probability 1 minus epsilon, the non-mutant is faced with the same non-mutant. Please notice that I don't count a concrete person in the fraction, because I assume that there are many agents in the population. So the fact that I'm looking at someone who is non-mutant only determines which strategy that person has, not how many others are left. It's always that there are Y minus epsilon non-mutants and epsilon mutants in our model. So, and that's a simple model, but it's really similar to many models of that kind. So it's really, I think it's a nice example to taste this model. So while this kind of model, so a non-mutant is probability 1 minus epsilon face a non-mutant, so then the non-mutant gets U of XX times 1 minus epsilon. That's the probability, and this probability epsilon, the non-mutant is faces a mutant. And the requirement is that the mutant always strictly suffers relatively to the non-mutant for any sufficiently small epsilon. Now, what does it mean? It means it's the same as to say now it's clear that the utilities which are preceded by the larger coefficient y minus epsilon, because epsilon is sufficiently small, those utilities have to be at least the U of yx has to be at least as large as U of xx, or strictly smaller. If it had been larger, if u of yx had been strictly larger than u of xx, then for sufficiently small epsilon, this inequality would not hold. So we have to have that u of x is either smaller, strictly smaller, and then actually does not matter what happens to the parts which are preceded by epsilon, because epsilon can always be taken small enough so that the inequality holds. Or if u of yx is equal to xx, that's the only other option, then we are left with the requirement that epsilon times y uyy is strictly smaller than epsilon times uxy, so dividing by the positive epsilon, we get that uyy is strictly smaller than uxy. So that we have to have this, and that's also enough. So that's the necessary and sufficient condition that for sufficiently small epsilon, we are going to have this. So we have now shown why this is the condition we want. And now, let us formally define what we want. So given a symmetric game, so for a couple, the options are BB and the utilities are symmetric. An evolutionary stable strategy, it's not a profile, it's a strategy, is of this game, is some strategy X and B, such that according to what we saw, what we require is that either that happened, so it's never worse to use X against another X than Y. So XX is always a Nash equilibrium. That's the same as saying that either this or this, either uyx is smaller strictly than uxx or equal. And if uyx is equal to usx, so if uyx is also a best response for y which is not equal to x, then we require this second thing, that uyy is strictly smaller than uxy. So we just simply rewrite this condition in the language of Nash equilibria. So we say that an evolutionary stable stable strategy, it's not a strategy profile, it's a strategy, because a strategy which is played by all the population, all the members, and that's evolutionary stable, because if some members a small amount mutate, it will be strictly worse than the others, than the majority. So an evolutionary stable strategy is X such that, first of all, X is a Nash equilibrium with itself, and if there is another thing, if there is another thing, which is also a best response, then that other thing has to be strictly worse against itself. So if y is non-equal to x, is also a best response to x, when paired with y, so maybe y is the same against x, but then x has to be better than y against y. In other words, it's always a Nash equilibrium to play this x against itself. If there is a mutation strategy, which is also the best response to x, then at least when the strategy is played, to that mutation strategy has to be strictly better than that strategy. Not necessarily a best response, but strictly better than y. Okay, so it's stronger than just saying that XX is Nash equilibrium, because they also have this condition. So that's the definition. And now let us look at an example, which is very classical. I think that example with a lot of description about the actual biological background and applications is described by Dawkins in his famous book, The Selfie Gene. And many famous economists worked on that, including Nobel Prize laureates like Maynard Smith. So I don't promise that they exactly do what we are showing here, but definitely that's a very important application. And please notice, even this simple formalism allows us to model important natural state. So imagine that you have animals which are the same, in the sense that they have the same options, and they compete against something, food, or males compete on females, or something like that. And whenever they meet, they have two options how they can behave. One is to be hawkish in the colloquial sense, so to fight over what they have actively if they face opposition, or just to take it if they don't. And the other one is to be dovish, which means to only take half, only take things if they don't face any opposition, half of that, and if they face any opposition, just to retreat and to withdraw and to take nothing. Now that's actually the model's real example. Shows why Dawkins speaks about why animals are not always aggressive, because it seems like it can seem that evolutionary is always better to be aggressive, but he says no, because being aggressive means that you can sometimes get in the fight and sometimes you can get hurt. Even predators sometimes don't want to fight with prey which they don't know. Actually, even predators can be killed by prey they do know, if prey is very strong and large. So the example shows mathematically, formalism shows why it's not always a best an evolutionary stable strategy to fight. So you have two strategies. If both are doves, they meet and they divide the value. Let's say the price is food equally, so half-half. The price is 1, normalized to 1, they divide it half-half. If hawk meets dove, so if person, again, they're similar people, simply that a person decides, or an animal decides, some individual decides to behave like a hawk, or behaves like a hawk. If it's an animal, it's probably not really a conscious decision, but it's rather differently taken decision, but the animal behaves like a hawk. Another animal behaves like dove. Hawk takes everything, dove is left with nothing. Symmetrically, if the first one is dove, the second one is hawk. Now, if both are hawks, however, they fight. So they equally divide the thing, but the value of the thing is reduced by C. I would say that I would just divide the thing equally and then just reduce by C the fitness because they fight. But somehow, this example is written this way, it does not matter. So I decided to show it that way too. Anyway, if they are two hawks, they do share the things equally, but the value, the fitness, is reduced because of the fight. And now, here, look at the formalism. So you have two players, so they're paired, the options to behave is the dove or hawk. The utilities are symmetrically described here, and if the results of the analysis follows. If C is stronger than 1, so the total damage is stronger than the total value of this price, in particular half of C is stronger than half of the price, then of course intuitively it does not pay off to be hawkish. So the unique symmetric equilibrium is the following strictly mixed equilibrium. So 3 is stronger than 1, then 1 over C is smaller than 1, so it's... So the dove gets more, the stronger the damage is. So in the limit, when C approaches infinity, the dove gets 1. So it's always dovish. When C approaches 0, it's always hawkish. So for general C which is strictly larger than 1, the unique symmetric Nash equilibrium is 1 minus 1 over C, And this also can be shown to be the only ESS. So the only evolutionary stable strategy here is not always fight. It's to do something in between, depending on the C. That's the interesting conclusion, or one of the interesting conclusions. Of course, if the expected, if what you expect to lose from fight is smaller than 1, then indeed the unique symmetric Nash equilibrium is to be always hawkish, and that's also the only ESS. Okay. So let us also remark one important thing that we can immediately observe, that if we have a strict Nash equilibrium, then it's always an ESS, because it means that it's first a Nash equilibrium. Now, second, there can be no other best response because it's strict. So the second condition always holds. This implication is vacuously true. So a strict Nash equilibrium is always an ESS. And we don't show it here, but in the book you have an example. The just Nash equilibrium is not necessarily an ESS. Well, otherwise you'll probably mention this, but it can be shown that just a Nash equilibrium is not always an ESS, but a strict Nash equilibrium is always an ESS. Okay, now, of course, let us just recapitulate so that we can nicely wrap up. So we'll look at some extensions of Nash equilibria. So that when we extend how we can randomize, we have mixed Nash equilibria, which can include, in general, strictly Nash equilibria, and correlate equilibria, which include, in general, strictly mixed Nash equilibria. Include in the sense that we, of course, need to identify the structure, because formally a mixed equilibrium is a probability distribution which can in particular have all the weight on some pure action, but it's not the same as just an action. So it's not the same formally as a Nash equilibrium, even if you have a pure even if you have a mixed Nash equilibrium which is deterministic. We just identify that, and they say that in that sense, a Nash equilibrium is always a mixed Nash equilibrium. And also by identifying the probability distributions in the mixed Nash equilibrium with the corresponding structure of the correlated equilibrium, as we showed today in a proposition, we can say that every mixed Nash equilibrium is a particular case of a correlated equilibrium. Now, a correlated equilibrium, we also prove that the extension correlated equilibrium always has this set of profiles which are convex. So we can say that the extension is convex, but it can in general be strictly larger than the convex hull of all mixed Nash equilibria. So it's not enough just to take all the mixed Nash equilibria and look at the convex hull. Now another direction of extension is the K-strong Nash equilibria. I guess the most famous, of course, Nash equilibrium is just strong. which is the n strong. So when you say the n is the number of players, so that's when you look about being coalition proof, so that the stability is not against only unilateral deviation, but also against a deviation of any deviation of a coalition of size up to k. And the large extension we've seen was actually not really an extension, because it was about evolutionary stable strategy rather than profile, but it was still a logically speaking extension of the ideas of Nash equilibrium for this random pairing, coupling, I think it's pairing, of agents from a population, and seeing which strategy is optimum and cannot be entered by any mutation strategy. Of course, these are just some of the most useful extensions. There are infinitely many possible extensions, and some useful extensions exist we have not mentioned. But I hope I've made you interested in those. Thank you. See you at the tutorial.